So, back to the fun part of the week. Any further questions about the time processing units? You look like you remember them with fear. You got the point what these kind of entities are good for? What's the main purpose of having devices like this into your embedded controller? Hello?
Things where timing is really important, where you don't want it being interrupted, or you just want it to do one task and stay doing that.
Mm-hmm. It's one of the many, many options to use concurrency to address hard real-time constraints. Because if you use concurrency in a clever way, that counts as clever, then you can decouple completely from your mainstream. This is a pretty extreme form of decoupling because you remember how they are communicating with the main CPU. They use dual-ported RAMs, which is a quite beautiful way of interacting in a real-time fashion. If you have anything else, you always have to consider what is the impact of this communication protocol I have with the other controller. So you outsource something to an external controller, but eventually you have to do some message passing, exchanging some information. Now, any form of exchanging information means that you need to synchronize, usually, with the other partner, and that can influence the real-time behavior on the other side. And there are very few communication protocols, interfaces, or any ways of communicating with somebody else which enables you to decouple it 100%. So you can guarantee that no matter how you exchange information, the other system will run always full blast without even noticing that there's communication happening. Of course, you need some kind of buffer for that you provide information and continue. You provide information, you continue. And somebody else can grab this information or not. You don't care. It doesn't make any synchronization or real-time difference for you if this information is being picked up or not. Then it's a clean, real-time capable interface. If you actually have to synchronize, you provide information, and then there's some kind of handshaking with your device. That means you're changing the real-time behavior, and that can make the analysis of your overall system significantly more complicated. So this form of decoupling is really important. Cool. So we briefly talked about time bases, and we will talk a lot more about time today. Glimpse forward into interrupt handling. Interrupt handling is, of course, a large topic in this course. And the interrupt handler itself, the interrupt controller itself, in modern microcontrollers is a pretty gigantic beast. Why? Why is that so complicated? How many devices do you have in a modern microcontroller? 20, 30, 40? This is the ballpark. How many signals and messages do you receive from each of these devices? A dozen apiece? 20? All of these messages can usually be programmed as some form of an interrupt. Now you have a system at your hand which can literally trigger hundreds of interrupts. And then you have one or two poor CPUs sitting in the middle of it, being potentially hammered by hundreds of interrupts. This is a nightmare and cannot be feasibly addressed in software. So what you do instead is you have an interrupt controller which pre-filters, queues, puts hierarchy onto that one, eliminates interrupts if they have been overwritten by other events. All of these things are handled for you by the interrupt controller, which, on the other hand, you of course have to program as well. So So the flood of interrupts in modern microcontrollers has to be managed someplace. This is the way of doing that. This is still a comparatively small one. What you have in your device, which will actually be handling, is a nested interrupt controller, which is even more complex than this one. So we'll spend some time reading data sheets here to get some idea how to get this under control. Okay. Yes, you have usually also a guaranteed latency for the interrupt controller itself, that you can guarantee that if you have a physical event hitting the controller from the outside, you have a maximum latency for the highest priority interrupt, so assuming everything else is of course unmasked, free to go through the whole thing, of maximally 20 cycles before you actually have the PC at the right spot and the thing is executing. Don't build too heavily on that, because in real life you don't have a single interrupt. You have many other interrupts, and the real problem is not to know the maximum latency for a single interrupt, but to handle the whole combination of interrupts which you may want to handle in your system, which will be much more interesting. So I addressed briefly that one here, and I nominated this as one of the biggest breakthroughs in embedded systems over the last 20 years, that you do have direct control, direct access to the internal registers of your CPUs today. This is not something which you use in your laptop or your desktop machine on a regular basis, because why? Because it's not a real-time system. There's not really a need for that. You can just simply stop your machine and look at the registers in your own calm time. But in an embedded system, that's a bit different. You need to have this monitored on an online basis. So those kind of interfaces which give you live access to the current register values, and you can live change register values there, is a pretty important interface to have. Okay. You can also produce traces. So imagine this whole thing is physically a very high-speed serial interface, and you have to program the Nexus controller on the other side what information you want. And this controller then pumps this information towards your analysis, your monitoring station, and you get traces which memory cells are being used, how they're being used, how the register values change, which gives you a beautiful possibility also to analyze the whole real-time behavior of your system, because you see live on the machine how tasks are entering and leaving the CPU, when is you see your schedule, your actual physical schedule, live while your machine is running. You cannot do this in any other way. You realize this? Actually, of course, you have some CPU monitor on the laptop, right? And shows you what processes are currently there. This is orders and orders of magnitudes detached from what actually happens on the machine. Those are all statistical information which you get there, which has been accumulated over the last 100 milliseconds. This is eternity for the kind of schedule precision which we are talking about here. You have to be a lot more precise than that. Okay, I don't want to go any further on the MPC 555, 565. Just as an example, we will go, of course, a lot deeper in the machine which you will actually be working with, which is not an MPC 555. Current CPU architectures in embedded systems. Do you have any feeling what is the common CPU architecture for embedded systems by now? What would you guess? RISC? What does that mean? I mean, I know what the word means, but what CPU core is that exactly? Or what type of core do you have there?
Simple instruction sets.
Sure. Well, but that was a cheap goal, which you just showed, because Do you know any CISC processors at all anymore?
Modern x86 is really discounting, isn't it?
Yeah, that's I mean, even the Intel processors, the x86 line, which is the classical, still alive CISC architecture currently on the planet, is slowly moving into a RISC kind of territory, which means the term pretty much lost its meaning, because you won't find, other than in the museum someplace, any other instruction sets anyway. So your answer is correct, but it doesn't say anything, because pretty much all processors are RISC processors these days. Have you worked with any concrete processors in your prior life for embedded systems? What were they? Never touched any embedded system in your life? Really? Never played with anything? Yeah. Well, of course, the Cortex M4 is still very fashionable, because you will get a Cortex M4, which is the smallest respectable ARM processor which you could use for those kind of environments. You will have a bunch of more processors on the board which you get. There are also Cortex M3. I think there are 2 more Cortex M3 processors on there. They're used for other purposes. But the machine which you actually will be working on will be a controller based on the Cortex M4, which is a classical ARM architecture. They are all 32-bit architectures which you will be working here. These 64-bit architectures are, as we speak, making their way into the embedded world. They're not available quite yet. You cannot buy, at least without dishing out unreasonable amounts of money, embedded controllers which are actually 64-bit wide at the moment, but this is unstoppable. This will be definitely coming very quickly now. Okay. Otherwise, you have the whole AVR family, the PIC family, the ARM processors, obviously, as you will enjoy, the Power PCs. The Power PCs have been living in the embedded world for a long time. For one reason, because this is one of the classical RISC architectures. They were RISC architecture based long before the competition used that, which made it much more attractive for hard real-time programming, because you could predict the behavior of these systems much better. And yeah, they are still used today, mostly for routers and environments like that. Cool. So let me finish this chapter with a few general remarks, how to interface with the real world. What are the possibilities for you now from a programmer point of view? Not from a hardware point of view, but from a programmer point of view. How can you interact with a piece of device, with a system which you want to squeeze data out? Status-driven, which means that you dedicate the whole CPU to staring at the interaction with the outside world. You do polling. You actively ask, is there something for me? Is there something for me? Is there something for me? Huh? And don't dismiss that. You will see this in real life more often than you think. And it's not a dumb idea by default. Depends what else is happening in there. Of course, if you waste several gigahertz CPU staring at a pin someplace, that sounds a bit unreasonable. But if you dedicate a small Cortex M3, which takes about 50 milliwatt if it goes full blast, to staring at a line, that may not be the worst idea on the planet. And then you can use the other CPUs to do more interesting things. Yeah. Everything else is a more complex operation, is somehow interrupt driven, but the target of your interrupt is not necessarily your CPU. You can set up your device that it gives you an interrupt by the end of an operation, and whether this interrupt is handled by your CPU or some other device is still open. Okay? What other devices could we have here? It could be handled by a DMA controller, for example. So you program your AD converter to trigger an interrupt, which is ultimately not going to your CPU, but your interrupt controller reroutes this to a DMA controller. The DMA controller will be activated. The DMA controller grabs information from your AD converter and stores it somewhere in memory. You can do this with your board as well. This is a classical way to interact with that one. Rerouting all the events which are happening in a specific I/O device to, for example, a DMA controller. Or to any other more complex channel-oriented device. A DMA controller can only shuffle data around, but you can also have, for example, the TPU devices, which we have here. You can also trigger those and activate those to interact on your devices. So, how long does it take to get any kind of response from your devices? If you interact with a network port, for example, and it's not exactly a 100 gigabit supercomputer kind of wire, if you interact with a network of some sort, what's the classical pattern when you interact on a network device?
You like the network stack goes up through the layers and it gets the data gets triggered up layer by layer.
Yeah, that's now you're explaining the actual network protocol by itself. My question was more with respect to timing. So if you write your user program and you want to read out or send data on a network channel, are you actually sitting there until something arrives? How long are you waiting? All these questions about how long do you wait, or do you wait to be called back when something happens, is something which you have to address on a daily basis if you work in an embedded environment or any kind of a physically connected system for that matter. Usually this is taken away from you by the operating system if you work on your desktop machines. Because if you do I/O there, what actually happens from your user program perspective if you do I/O? Anybody ever done I/O? You call something on the operating system. What happens to your program? What happens to your process?
It just gets to the top level. It only just deals with that nice interface.
No, that's not what I mean in terms of timing.
Does nothing for a while.
It does nothing for a while. What does the operating system do to your process? It suspends it, of course. Right? You do I/O with your programs and you're out of the CPU immediately. Are you aware of this? Why does this make sense?
Because even if the CPU wanted to do the best thing for the sake of the process, it's still the operating system is carrying out the task wanted by that process. So if the process isn't doing anything, because it's called, it's asked the operating system to do something in the form of network stack, it itself isn't doing anything, but really it as a whole job is still doing stuff. As in the,
what do you mean by doing stuff? What do you mean by doing
as
stuff?
in, you can still have the operating system fully fledged on helping out this process, but the process doesn't actually have to do the work because it's the job of the operating system.
If there is actually something to do at the moment.
Well, we were accessing a file or sending something over.
If you access a file, for example.
Oh yeah, I mean if you make a read, you go for the request out, you go wait for the hardware to respond, and you get the data back to you, and then come back through the operating system.
Exactly.
The process has to be, initialized again.
Yeah. So you, from a non-embedded, non-interrupt oriented, not real-time programming perspective, working on top of an operating system, on top of a non-real-time operating system, you don't see any of that. You just request information from a file, and it looks like this just happens now. What actually happens is something different. namely what you just said. You call the operating system requesting information from your file. The operating system sends out the request to your mass storage device to maybe start spinning up the drive, maybe getting the head into the right direction, maybe doing something there. But this will take time. This will take a long time, potentially, to do that. A very long time with respect to a 3 gigahertz CPU. Which means that this will be requested. Please get this information and this data in. But you will automatically suspend your process and your CPU will be given to somebody else. Then the data comes in, interrupt is going to be triggered, process is going to be changed, and you can actually read in the data. Now, on an embedded device and in a real-time world, that's your job. You don't have a non-real-time operating system doing that somehow for you. You have to actively control it. You have to make a decision. Will I be standing by? Will I be staring at this I/O line until something comes back? Will I suspend myself? How long will I suspend myself? Do I want to be reawakened after some time? Do I want to be reawakened after a specific event happens? Those decisions have to be made by you now. Okay. So you need to analyze what is the timing behavior of my system, the device which I'm interacting with. Is this a system which has a predictable timing behavior? I know, for example, if I ask for information from a keyboard, the keyboard will tell me after a certain amount of time whether there is something or not. I know the protocol which happens there. It doesn't tell me whether, I cannot predict whether the user pressed anything, obviously. That's the unpredictable part of it. But you have possibly a predictable time to know how long it takes to get confirmation or not, whether there is something there. From mass storage device, much harder to predict. How long does that take? For each of these devices, this answer is very different. You need to be aware of that. Okay. Now the problem is, of course, that some of these answers which you will be getting there will be along the lines of, hell, I don't know. How long is it going to take until the user is going to press this button? And you go, maybe he never pressed this button. How can I design my real-time system based on unpredictable events? Of course, your user is a classical example of one of the most unpredictable events you can possibly have in a real-time system. But there are many other unpredictable things which can happen there. And to embed the unpredictable into your predictable real-time system is one of the many challenges which we will address here. Do you have any idea at the moment what to do there? You have your beautifully designed hard real-time system which runs like clockwork. Everything is CPU cycle precise, nothing gets this thing out of whack. And then your boss comes and tells you, well, I also have to handle these keyboard interfaces and these user inputs and these network interfaces. Make this connect to your beautiful real-time system. You look at your beautiful real-time system clocking away completely predictably, and you feel bad. How do I combine these things without just messing it up? Because if I now, in the middle of my real-time system, put a single instruction there, wait for the key press of my user, it's screwed it all up. It's just dead. It cannot be that simple. But how do I make sure that I can handle that and keep my real-time system predictable and sharp at the same time?
What do you mean by predictable and sharp? Predictable and sharp? If you mean
I can predict the exact sequence when what happens on a CPU cycle precise basis. If I would be able to do that, it's a completely predictable system.
But because we have humans, we can't, like, why are we, say with the example of wait till the key press, right? Mm-hmm. Why are we even bothering trying to predict when the thing pop up the screen and we press the key? You can know that within some certain time frame after a key press pop up the screen. But
okay.
Say how it is overall, so that involves working out predictability human, which is...
Yeah, you're now assuming that every system at some point will involve humans. That's one way of thinking about it. So my system will be unpredictable anyway. Why are we having this course in the first place? It will be unpredictable anyway. But think about it from a different perspective. Assuming that you have, say, a nuclear reactor. And there will be control circuitry for this nuclear reactor, which is completely precise, not disturbed from anything outside. And it has to be, because that's just physics. If that thing is not being controlled in those irregular intervals, all hell is going to break loose. There's no choice about this. So you have a core of elements which are these completely predictable real-time control environments. But you want to interface those also with your operators, sitting in these beautiful console rooms where you have these displays and you can control the reactor as well. So you have always this dichotomy of you have a core of a hard real-time system which you can design by itself, which would work if there wouldn't anybody messing with it, beautiful on its own. But you usually, as you're right in that, usually will have to at least report to the user at some point. And usually you want to give the user also a button to, for example, shut it down. Right? If your real-time designer comes back to, no, I'm refusing to give this nuclear reactor a shutdown button, it will mess up my real-time constraints, that may not be a great idea. Right? But you see, the things have to come together at some point. If I'm just saying I wave my hands in the air, the user can actually request stuff at any given time anyway, and this will mess up my system anyway. Why bother? That's not going to cut it. I still need to fly my airplanes. I still need to control my planes, my trains, my energy grids, etc., which are subject to hard real-time constraints. You have to combine that. And don't be too disheartened about this. There are clear and nice methods to actually do that without messing up your real-time constraints. A number of ways of how we will actually learn here how to do that. Okay. There are two main directions this answer will be going in the following chapters of this course. One is the unpredictable things have to be synchronized with your real-time system. So there are asynchronous, there's unpredictability in there, and you have your predictable synchronous environment, and you have to synchronize the unpredictable stuff into that system. That's one path to go. Or the other path to go is you decouple. For example, the dual-ported RAM interface, which we had before. You just leave the predictable system completely alone and only communicate and interact with the predictable system by means of interaction which cannot get it out of whack, which can control it, which can give it information, steer it in the right direction, but not destroying its real-time integrity in the process. That's another path to do it. Keep these things separate. Okay. Which usually requires more hardware. And what are our requirements for language requirements for real-time and embedded systems? We need to be able to be very specific to actual protocols and formats of our hardware interfaces, of our hardware devices. And we saw a few possibilities to do that. You can leave it to the compiler and do it by formulating data types. You saw these bit-aligned records which are interacting with your hardware, and then you leave it to the compiler to actually do that, to set the bit to the right value. Or you say, I don't want to have compilers, I do it all in machine language, and do my bit shifting and masking myself. What is the ADA compiler going to do for you if you actually formulate all of these beautifully bit-aligned records and strong type-safe system? What code is the ADA compiler producing for you? Exactly that kind of bit shifting and masking massacre, which you can also program by hand, only that there are a lot less possibilities this can go wrong because you are in a strongly typed environment. Or if you do it by hand, there is nothing but bits and integers. And everything looks exactly the same. Huh? Okay. So what you want is not very different from what you would want from other programming environments. You want to be able to be very specific while having the possibilities to use abstraction to have significantly complex systems at the same time. Because your systems are very complex, like almost all software systems. That doesn't make it any different if you work in the real-time world. But the requirement to be able to be very specific is here even more dominant, because if you're not able to be very specific with your interfaces, you are pretty much doomed in the real-time world because you cannot communicate with your devices. Okay. Cool. That concludes the overview of controllers, interfaces, AD converters, transferring electrical signals into your computer environments. This is what we have done in this chapter, with foreshadowing a number of things which will be coming now in the following chapters.